algebra to help you kind of correctly finish this problem off. Again, as we start thinking about how do I know what tests to do, right? And we're going to get to a bunch of tests, right? So how do I know what to do? One of the ones I like to do ratio test on a lot of times is if there is an n in an exponent, right? So if there's an n in an exponent, okay, a ratio test is typically going to be a really nice one to do because, again, as we see in the last day or two doing this, right, that's going to leave us with a constant somewhere, right? Because I'm going to have one more exponent, right, with the same base somewhere, okay? So really good idea, typically in my opinion, of doing that. So that's one of the key things I look for. All right, is a ratio test a good one to use? Yeah, if I've got an n in the exponent, which I do. Okay, so it typically is a nice one to use. So this would be 3 to the n plus 1, right, over 5 to the n plus 1, and then plus 1, and then times 5 to the n plus 1 over 3 to the n. Okay? Now, unfortunately, the math's not just straightforward with the 5s, right, because it's 5 to the n plus 1, right? Okay, so we got to just use a little bit of work. This 3 to the n is going to cancel, leaving me with 3 in the numerator, right? Okay, and again, that's what I'm talking about, right? That I'm going to get this extra constant either in the numerator or denominator, right? And I'm kind of assuming that the denominator is going to go to 5, right? Because this plus 1 is going to be pretty insignificant, right? So again, I got to kind of get this inkling already of what I'm going to get as an answer. But really, to do it accurately, what do I have to do?
Factor out of 5 to the n.
Yeah, factor out 5 to the n. I saw a lot of people doing that, which is really good. So I get 3 times 5 to the n, and then this would turn into 1 plus 1 over 5 to the n. All right, I'm going to factor a 5 to the n out of here. This becomes 5 plus 1 over 5 to the n. 5 to the n's cancel. Now take your limit as n goes to infinity. So again, this big idea we've been working with literally all year, right? So basically the beginning, of this course to here, being able to factor kind of something common out to be able to cancel and simplify while involving a limit as you go off to infinity is still going on in this course, right? I mean, this is coming through forever. So this becomes 1 plus 0 over 5 plus 0 times the 3 up here, so this is equal to 3/5, right? So 3/5 is my L value, right? And since 3/5 is less than 1, the series n equals 0 to infinity of 3 to the n over 5 to the n plus 1 converges by ratio test. Okay? And so that'd be your good work, right? So this would be what I'd expect if you're talking, nice solid work, right? Clear, concise, exactly what you need to, to show to be able to justify. This would do it. Right? So again, pretty straightforward. Again, really nice ratio test to use when I've got an n as an exponent, right? It's a good thinking idea to do. Okay. Again, there's no x's in here, so I'm literally looking at just this series, right? This is one series, right? What does this series do? If I started listing out numbers, right, put 0 in for n, and then plus 1 in for n, and plus 2, right? It's going to be just some numerical series, right? And the question simply is, does this series sum to a finite number or not, right? Does it converge or does it diverge? In this case, this series converges. Again, I don't know what it sums to. Okay, I don't know the value of this. Okay, again, that's difficult to figure out lots of times. Okay, unless again, it's not geometric, so that doesn't work. Right, so I don't have a formula for it. Okay, I don't think when I look at it, I don't recognize that as some Maclaurin series. Definitely not. Right, this isn't a Maclaurin series going on. Right, so even if I listed the terms and seen it, because I wouldn't see some common pattern going on, so I'm not going to know that. Which really leaves me, for the most part, to kind of look at partial sums. Right? I literally have to find what S of 1 is, and S of 2 is, and S of 3 is, and S of 4, and see if I could somehow create a formula for what the partial sums are, and then find the limit as n goes to infinity. Okay? Which I'm guessing it would be hard to do, but I wouldn't know until I tried it to do it. But that's kind of about where you're at for doing it. Okay, so that'd be one route. Okay, other routes people went on this. Yeah.
We compared it to 3 over 5 to the n, which is geometric with an r value less than 1, so it converges.
Okay, so 3 over 5 to the n is what compared to this?
Greater.
Greater. Yes, right? So basically I've got the same numerator, right? And then the denominator here is 1 larger than the denominator there, right? So bigger denominator, smaller fraction, right? So I got this true statement here, okay? And since the series 3/5 to the n converges as a geometric, right? Then the series n equals 0 to infinity of 3 to the n over 5 to the n plus 1 converges by the direct comparison test, right? Right, so they found a larger, right, function, right, that they knew converges, right? Therefore, the smaller one must also converge. That's what that direct comparison test says, right? And again, it's just got to be, make sure it's got to be larger from some value and on, right? It doesn't have to be larger right away, okay? It might take a couple of terms for this series to be larger than this series, and that's okay, right? So as long as it's for some big N, capital N on to infinity, we're good, okay? Because again, the first couple of terms are just going to be finite values anyway, right? And so it doesn't mean, it doesn't matter if the first 3 finite values are larger for the one series than the other. They're just finite, values, right? The real question is, as you go off to infinity, right, do the terms get small enough for it, for the whole series to sum to a finite value, right? And as long as from some point on, right, from some capital N value on, right, these terms are going to be larger than these terms, then it's going to converge. Good. Okay. Any other ideas we could have done? A really similar combo to these two we talked about last chapter. So we talked about a direct comparison test. We also talked about a limit comparison test, right? Right? Which would be finding the ratio of 2 series, right? Specifically the series we're looking for. And what series would I compare it to?
3 over 5 to the n.
This series, right? Right, so a third option for this one, right, which is going to look really awfully similar to what the ratio test did to this one, right, would be finding the limit as n goes to infinity of 3 to the n over 5 to the n plus 1 over 3 to the n over 5 to the n. Right? So then this kicks up, right? And this looks really, really, really close. And so I get 3 to the n over 5 to the n plus 1 times 5 to the n over 3 to the n, right? And 3 to the n's will cancel. You can factor a 5 to the n out of this. You could take one derivative, right? And then the 1 would go away, and then these two would be the same, right? The derivative of 5 to the n would be the same as the derivative of 5 to the n plus, 1. Let's just stay consistent with what we did in the other one. So 1 plus 1 over 5 to the n 5 to the n's will cancel, and what's my limit going to be here? 1, right? So the limit as n goes to infinity of one function, right, or one series, general term of a series over another is 1. What does that tell you about the two series? They do the same thing, right? It's that kind of the same rate of growth, right? If you get that constant, yes? Right, so we get that constant, so go back to, last chapter, right? Relative rates of growth, kind of, that was our kind of connection with that, right? You get a constant, that means they do the same thing. And since, now we're just back over to here, right? So since this series converges, because it's geometric, this series is going to converge by the LCT, right? By the limit comparison test. Okay? So why is that important? Well, Tanner's idea wouldn't work if I did what to this series?
3n plus 1 over 5 at the end.
Okay. Alright, so did that with it, right? Now his idea doesn't work anymore. This one, right? Because the statement is flipped, right? But what will work? Limit comparison test. As will still the ratio test as well with this, right? So either one of those would be good ideas. Okay? So again, as we talked a little bit the other day, or last chapter, really briefly about the limit comparison test. Limit comparison test is, to me, a much nicer test than the direct, because it's a little bit more flexible of what's going on, right? And requires a little bit of work. This is more just kind of making a statement, right, and then concluding. Here, you obviously had to do some work to, justify that the limit was a constant. Okay. All right. So what we've got right now, just adding some things to our list, just to kind of remember, right? So we've got our nth term test, which we wrote down already, right? So that was the limit as n goes to infinity of a sub n doesn't equal 0, and the series a sub n diverges, right? Right? Yes? All right. We've got our ratio test. All right. All right, and so our ratio test is the limit as n goes to infinity of a sub n plus 1 over a sub n equals L. If L is less than 1, the series a sub n converges. If L is greater than 1, series a sub n diverges. And if L equals 1, inconclusive. Okay. We got our DCT, or direct comparison test. All right. If B sub n is always greater than or equal to A sub n, and for n greater than or equal to n, right? So for some n value and on, right? And B sub n converges, A sub n converges. Or if B sub n is less than or equal to A sub n, and the series B sub n diverges, right? And A sub n diverges. Check that, make sure I wrote that right.
What is the 4n is greater than n?
So again, what I was talking about is that as long as for some n value, some capital N value, so for some n value, this series terms are always bigger than this series terms, then this is going to work. Okay? Again, it doesn't have to be what the little n starts counting at. Okay, so again, the smaller series might have larger terms initially, right? The first couple of terms in this series might be bigger than this, but as long as for some n value, at some point in time, for one of these values, when I start listing out and comparing terms, right, at some point in time, and then from that value on forever, these terms are always larger than the other comparable terms. That's what we're looking for. Okay, so there are a lot of times it's right away, but there are times that it might take a term or two for that to, happen. Right, so here b sub n is bigger, right? Right, so therefore if the larger series converges, then the smaller series converges, right? Here b sub n is smaller, right? So if the smaller series diverges, then the larger one diverges, right? Okay, so again, that's what that is saying, right? And so b sub n is the one I know, right? That's the comparable series, right? That's what I'm comparing it to, right? So for our case, b sub n was 3/5 to the n, right? And a sub n is our series we're trying to find the answer to, right? Okay. Then we got our LCT, right? Okay, so then we got this one. All right, so if the limit as n goes to infinity of a sub n over b sub n equals a constant, not zero, right, a non-zero constant, then the series a sub n and the series b sub n do the same thing. Meaning, if b sub n converges, a sub n converges. If b sub n diverges, then a sub n diverges. And again, feel free to write that, right? You need to write more details than just what I wrote. If this does, you're not going to be able to look back at this and know what it means, what I'm talking about when I say do the same thing, then write. If the series b sub n converges, then the series a sub n converges, right? If the series b sub n diverges, then the series a sub n diverges, right? Okay. All right, so again, you got to write notes for you, right? Okay, you got to write it so you understand and come back, look at it, and get it, and can apply it and do it. Okay. All right. So what happens here? If I get infinity, what does that tell me about b sub n and a sub n? A sub n's larger, right? Okay. So therefore, b sub n, which is the one I know, right? Remember, this is all. B sub n is the one I know what it does, right? Again, I'm not comparing it to something I don't know what its answer is. That doesn't do me any good, right? So don't pick a series that you don't know whether it converges or diverges, right? That's pointless. Okay. All right. So b sub n smaller. Yes, in this case, right? So if the smaller one diverges, right? So what I know here is if b sub n diverges, then a sub n diverges. Right? If b sub n converges, what do I know about a sub n? Nothing. Right? For this case, right? Third, you got the other case, is if this goes to 0, then b sub n converges, right? It's the larger one, so b sub n converges, then a sub n, series a sub n converges. Okay.
No, okay, so that is, larger. We don't know.
Hmm?
We don't think so that is larger.
No, b sub n is going to be larger because I'm getting 0. All right, so the larger one's in the denominator. So if the larger one converges, then the smaller one must converge. Right? If you get 0, that means your denominator is bigger. All right, so again, there's still definitely inconclusive stuff here, right? Right, so I mean, there's some stuff that's not conclusive, right? Didn't do me any good, right? There's inconclusive stuff here, right? If I get 1, right? There's inconclusive stuff here if I get 0, right? There's inconclusive stuff here if it's, doesn't work, right? If what I had, is the converging one, but it's the smaller one, right? So again, there's lots of, bless you, there's lots of, crap, this test doesn't work, right? This test is inconclusive. This one's inconclusive. This one's inconclusive. This one's inconclusive, right? There's a lot that is conclusive, though, about them, right? Okay? And as you saw here, this one problem could have been solved how many, or justified how many ways? 3, at least. Bless you. Right? At least 3, right? Maybe there's some other tests, right? But all 3 of these, tests so far, the only one that didn't work is the nth term, right? Which it better not have worked because we found that this series converged, so hopefully not, right? As n goes to infinity, again, the 5 to the n is going to dominate the 3 to the n, so it's going to go to 0, right? The denominator is a lot bigger than the numerator, right? And again, figure that out through one derivative and then a little bit of math. All right? Yes? Good? All right. Let me try. Let's do this one. So figure out what is the series from 1 to infinity of 1 over n plus 1 do.
So we just solve these 4, so